Hey everyone, good evening. My name is Dheeraj. Welcome to my talk. I used to be the head of engineering for a startup till recently, and currently I'm looking for my next workplace. Um, you know, Throughout my career, like I've been doing what is generally called full stack engineering. It's essentially just a nice way of saying that I can write code that crashes in every single layer of your application. Some of the companies that I've worked in have been small, some of them have been large, but no matter the size or maturity, right, there is always this dichotomy of front end versus back end, right? I've experienced that in pretty much every workplace that I've worked in. Whether it be a single person who is writing, both sides of this equation on any given day, or whether it be two separate teams geographically distributed across the continent, across the world, the commonality is these three things. These three things. It's like they all maintain state. They all manage the network communications in between, and they all facilitate this using glue code, which you have to write manually or generate or something like that. But ultimately, it's still code that you sort of have to maintain, right? A long time ago, before all of this, I was an early employee in a company called Quintype, which I think a lot of you folks might have heard of. We famously used Clojure for quite a few things over there. It was definitely a formative experience for me being there. I learned a lot. Uh, and and I worked there for like 4 years. To give you an idea of when this was, right? At the time, React was not even 2 years old, and Kubernetes had just been released, right? It was definitely a wild time to be around web technologies, right? Everything was in flux, and we were all just trying to figure out where all of these technologies are going to go. We did the same things I spoke about. We maintained state, we managed the network communications between front end and back end, and we facilitated that using a lot of glue code. Okay. It has been 9 years since then. In that time, I think there have been, we've seen many technologies emerge and evolve to help us do the same things, but maybe in slightly different ways. Maybe make it slightly easier for us. Back in the day, we still had REST APIs. We are definitely not that old. So we still had REST APIs, but I think GraphQL came into the picture much later. And we consumed these using libraries like Apollo and Relay, to name a few. And or maybe even just a regular fetch, XHR kind of a thing, We rendered these using React.js back in the day, which was super new at the time. And now we have better technologies like Next.js. Okay. But when I start to think about these technologies, I often keep wondering, are these really necessary? Like a lot of this felt like unnecessary cruft that was just bolted onto what I really wanted to do, right? Or at least speaking as a full stack engineer, all that I wanted to do was something like this, right? I wanted to query a database, get the results, and render something with it, right? It was as simple as that. Now, it does get a lot more complex in the real world. Like you have data bindings, this, that, data flow changes quite a bit. But ultimately, it all comes down to some variant of this or the other. Right? I call this my pipe dream. Right? The reason why it is a pipe dream is simply because of the network in between all these different layers. And we don't have this right now, and I don't know if we ever will, but that's what this talk is about, right? By the way, Abhinav gave a fantastic talk about functional programming patterns just earlier, and I wanted to give a shout out to him because one of the points he mentioned was how functional programming prefers explicit compared to implicit, and how it's easier to read and so on. He spoke about a bunch of benefits there. This talk is all about magic, right? So it's a complete antithesis of that. So back to history, right? It seemed like things were changing when React 18 came about. So React 18 via Next.js 13, I believe, they introduced something called React Server Components. It essentially let you have components that would run on the server side of things. So essentially host a node server and it runs React, which runs your components. You could do anything you wanted, like query a database, make an API call, and then rendering your DOM as a function of that. You could also have your regular React components, client-side React components, which the user would interact with and take some input or the other, any sort of interactivity that you can see. React 18 came up with this compiler that essentially let us sort of interleave both within the code. So as you can see here, you could have the S as a server component and the C is a client. So you could have a server component that renders a server and a client, and it sort of goes all the way down. React's compiler made sure that, and this is, if you can recognize this is essentially a graph coloring problem. And React's compiler made sure that it separated out the server colored bits separately into one bundle, the client colored bits into another bundle separately, gave you both of them so that you could distribute it however you wanted to. And in the runtime, it will make sure that it manages the data flow in between both of them fairly seamlessly. Now, and to sort of activate this, all you needed to do was, for a server component, you needed to put a use server line on top, and for a client component, you need to write use client. So that's a directive in JavaScript. It left a lot of things unaddressed. Like, for instance, if you wanted to maybe refer to another part of the server, something that wasn't part of this particular chain of components that you are in, this tree of components you are in, you would, from the client, you would have to make a HTTP call using XHR fetch, the same way that you're doing right now. Not really much of a difference, I would say, right? For a brief period, there was also a lot of excitement around something called the Next.js server actions, where you could essentially define a function and run it on the server. You could, again, do stuff like API calls or manipulating your DB in some way, and all of that was pretty great. So you could write the function in your React code. You could call that from your client just like a regular function that you would call, but it would execute it on the server, right? Which seems like a pretty exciting idea when you hear about it. But the excitement, to me at least, died down a little when I realized that it was recommended for use only for mutations and not for querying, right? I think querying is a fantastic use case for something like this, but it was essentially available just for mutations. At least that was the recommended use. My excitement died down even further when I realized that these server actions are essentially synchronous. They are not asynchronous. So which means that if you had two clients connected to a Next.js server at the same time and they were calling the same action, then one client will have to wait till it's processed for the other. In all of these technologies that I've seen in the last several years, nothing has really felt like a breath of fresh air. Nothing that feels like going on an adventure, right? Feels like an entire world of possibilities has opened up, and it is up to you to explore the technologies and just have an adventure building something worthwhile. And that's sort of when I found Electric. It's not a library or a framework or anything, but it is, I think, an entire system in itself. I think that's the easiest way to describe it. The makers of Electric, it's built by a company called Hyperfiddle, and I think I spoke to Dustin Getz, the founder of Hyperfiddle. I think they have a small team of engineers working on the problem. I think he mentioned somewhere that it is his 7th attempt building something like this. It's something he's been trying to build for a long time, many years now, and this is the 7th attempt, which is, I think, very commendable. Hyperfiddle calls Electric, they call it a web programming language. So let's sort of see what that looks like, right? So this is a plain Clojure example. So as you can see, we have a bunch of DB calls being made, and ultimately that renders a table full of t-shirt orders, and it's also like a inline editing kind of a thing. So you get to display the ID, display the name, the size, and you get to also change around in whatever with the HTML controls that are provided. It's a fairly common sort of a use case. There is some interleaving here and there. Like for instance, you can see that the option for the genders filter, so it basically takes in a filter as an option, but the shirt sizes drop down that is shown essentially takes in the gender as an option. So which means that whenever you change the gender in the drop down, you want to show different shirt sizes, right? And that's all fetched from the database. So it's a fairly common sort of a Clojure component that you can write. So this is actually an actual working Electric code, right? What you had to do here, and if you sort of look at the changes, we've essentially wrapped our queries with eServer, our rendering code with eClient, and we converted our functions, the funs, to eFuns. And the earlier code which you saw is probably not something that, it's something very similar to my first example, which is what I call the pipe dream. It's not really something that I could have built. It might have probably been like server-side rendered and a bunch of things like that. But it really wasn't possible with the kind of tooling that we have right now, or the kind of web frameworks that we have right now. This, on the other hand, like I said, is actual working Electric code. This renders the data from the server. So let's see how it works. It calls the DB functions first. So it fetches the orders, it fetches the genders and the shirt sizes, and renders the initial page. And whenever you mutate something, whenever you make any sort of changes, the changes are sent to the server, and they are whatever queries are there are fetched again with the necessary filters that you have put in based on whatever inputs you have given, and the whole thing is re-rendered again. Okay. By the way, I don't know if you notice the similarities to React Server components that we spoke about earlier. There, all you had to do was you had to use a directive on top of your JavaScript file, and here you replace it with Clojure functions. You just annotate your code saying what should be run on the server and what should be run on the client. So how does something like this work? I guess the one word answer is it's like functional reactive programming, FRP, all the way down. So Electric is an entire system that basically compiles the Clojure syntax into a data flow signal graph. Okay, and that's a DAG. The DAG is then compiled into missionary signals. So missionary is this library which is written by the Electric team itself. It's like the core of Electric Clojure, which primarily deals with handling the execution of the code that you've written, right? So it sort of implements the reactor pattern and it handles the execution side of things. The compiler, which is part of the Electric Clojure, colors the AST, which we have spoken about before, into the server and client regions, and it sort of identifies what are the network calls that need to be made. Like for instance, if you end up changing the value of the gender field, you have to go to the server, make an API call, and then return with the new values of the shirt sizes field, right? So these network calls are identified automatically because you've annotated what should be run in the server and what should be run on the client. Now at these network calls or network transfer points, as they call it, the entire environment, like not the entire environment of the server, but the environment that is just required to render and keep this particular page up to date, this particular component up to date. Now that environment is serialized and streamed to either the server or the client or whatever, to basically the other side of the equation. This transfer synchronizes the state, the runtime state that is available, and it essentially enables something they call distributed closures, right? So what if you could write a piece of code, make a part of that work in the server, part of that work in the client, while you being extremely seamless about the way that you've written it in. And making it work in this way is actually quite a challenge, because making it work for simpler statements is obviously there, but making it work through anything that Clojure itself supports, making it work through recursions, making it work through anything else, any other asynchronous features that it has, making it work with signals, streams, it's all pretty difficult. And the Electric Clojure team has sort of put a lot of work into making this work. Their primary concern so far has been accuracy. Right? They wanted to build something that is provable, that's something that works accurately, while not caring too much about the performance. It is already really fast. I'm gonna show you that anyway during the demos. It's already really fast, but I think that they're also putting in a lot of effort into making it work even faster. So they've really not started on the performance bits, but I'd be really curious to see how something like that would sort of work. So one way to look at this whole thing is Electric is a networked programming language, something that's really aware of the network, where you write regular Clojure code just the way you would, color it as server, client, whatever, and then Electric will make sure to distribute your control flow across the client server boundary. The tools that they've sort of built for this purpose are fairly extensible, in that even when you read some of their code or some of the documentation, they say that they always use the word nodes, while the client server is just one type of node that you can use, which basically means, hypothetically, could you use it across two different servers in like a horizontally distributed kind of situation? Maybe you can. Currently they're not doing it, but I think from looking at the code, definitely seems like that's something that should be possible at some point. So we mentioned signals. So let's talk a little bit more about that. So signals are essentially objects that have a certain value, and components can render themselves based on the values that's part of the signal. When these values change, only the components which are listening to those values or dependencies of those values listening to those signals or dependencies of those signals will need to re-render. Now, you might have heard of the term fine-grained reactivity in a lot of these new age front-end frameworks, or you would have heard fully reactive. Those are all terms used to basically describe that you are using signals underneath, right? That's all signals. This sort of unlocks a lot of performance benefits by virtue of it being lazy. So if you sort of look at how React works, React does something that we usually call overcomputing. That's the general term used to describe the model that React does, wherein even if one particular item changes in like a collection, React sort of has to go through every single one of them, and it needs to figure out which one of them has changed by usually doing like a shallow compare, and that's why they need the virtual DOM and all that stuff. But a lot of that is not needed if you have the fine-grained reactivity. It knows exactly which piece of which data has changed, and it knows the dependencies for that piece of data, and it knows how to update all of them by re-rendering them, right? Its power is unlocked even further when you look at computed properties. So not only is you can have signals that are functions of other signals. So when the base signal changes, you can have computed signals change as well, and you can have components that render that, right? So sort of unlocks a lot of these options just by the laziness, right? Now that's the keyword. If you're familiar with React, actually if you're only familiar with React, then signals are probably sort of blowing your mind right now. But in rest of the modern web development world, if you've used like literally anything else, then signals are just normal. It's like day in, day out, you just work with signals. It's just the way things work. It's a signal here, signal there, and not really a big deal. Currently, React is probably the only modern non-signal based framework that is out there. Literally everything else just uses signals. I mean, I forgot one, obviously. Almost missed that. So Electric is entirely driven through signals. So what Electric essentially enables is it essentially helps you create a stream of signals. So the entire stack of your application, right from your database all the way till your front-end rendering, to be essentially driven by signals. And that is a really powerful methodology to sort of take for Electric. Okay. Electric is in alpha right now. So it's in alpha 2 really. And they've released a bunch of really cool demos. So I just wanted to show you some of them. One sec. Yeah. So this is the first one that I have. So this I'm essentially running it from my local machine, but there is a hosted version as well that you can use. If you can sort of take a look at the code, right? One sec. Yeah. So as you can see, you have the same code running on two different places. You have so let's you find out what is the current timestamp. Scroll up. Yeah. Okay now? Yeah. So it basically lets you run the same code. So this example, you run the same code, which is get the latest timestamp, in both, it runs on both the client and the server. And whenever the server gets changed, it is passed down to the client. And you have a small piece of code that basically figures out the delta. The delta, as you can expect, is both the latency as well as any clock skew if you have something there. When you run it on the server, it sort of gives you a better response. But this is really cool. Like, this is basically data, and this is getting updated at, if I'm not mistaken, 120 hertz. So it essentially gets updated 120 times per second, which is, I think, really cool, and sort of shows you the performance that is that FRP and Electric Clojure are sort of capable of. Okay. The next one, which is, I guess, slightly more complicated than this, this is definitely a naive example, is the chat application. So let me sort of bring that up. Okay, so let's sort of see what this does. By the way, that was supposed to be hello. By the way, it's not. That was a typo. Yeah. So let's see what it does, right? So you get to. This is a proper sort of a chat application. The data is, as you can see, stored in an atom on the server. So which means that whenever a message is sent to that server, whenever that atom is updated. And this is an electric atom. So it's essentially going to be streamed to every single client that is connected to it. So it essentially simulates a chat room that you have. There is some front-end code, some Clojure script code that essentially makes sure that does a bunch of sanity checks and whatnot, but essentially takes the user's input, and whenever that changes, the atom is updated, right? So fairly sort of straightforward code that you would expect to write. But what is sort of mind-blowing to me is that you can sort of write the whole thing within one single file and it just works, right? So let's just see like a quick demo of that. Am I typing it right? Yeah, there you go. So when you sort of do that, so this data is not just rendered in the client, it's essentially sent to the server and rendered back. And one question that you may have is, how does the server communicate with the client? You didn't really see like a HTTP call go through or whatever. So what happens is that the client and the server essentially maintain a persistent WebSocket connection. So any changes that the server wants to stream down to the client, or any data that the client wants to stream to the server, it all happens via the WebSockets. Okay. So these are the two sort of demos that I wanted to show you, and it just having to run the client and the server in the same code base, or at least in the same file, is something that I didn't really imagine to be possible. Like, at least not as seamlessly as this. I know it's sort of possible in other in like quite a few other paradigms that are available, but definitely not as seamless as this. Okay, so let's get back to the presentation. So at least to me this seems really magical, right? Let's explore how this works a little bit more. So let's sort of take a look at Electric's architecture. So what you write is essentially Clojure code that is annotated and surrounded with a lot of primitives that Electric Clojure provides. So you write Electric Clojure, which they call it a separate programming language in itself. You write that in your regular Clojure files, so Clojure or Clojure script files, that is taken by the Electric compiler, and it essentially produces something they call the Electric bytecode. So they have their own AST and bytecode that is required for this to work. So they transform it into that. Now, this produces two different bundles. So you have the server bundle, which is a jar, which is run by your regular Clojure VM, and then you have your client bundle, which is a JavaScript file, which is run by your Clojure script runtime, right? So both of them are generated at the same time. So it's up to you to figure out how you want to distribute it. So you can run it using your favorite server on the server side, while on the client you can distribute it via either just your regular file server, or you can distribute it via a CDN. That's all up to you. Now, this bytecode is processed by the Electric VM, which is a separate VM that they have written on top of the Java VM, and also the Java Clojure and the JavaScript VMs that exist right now. So it essentially, at the compile time, it has a network planner, which is the part I was talking to you about. So it separates out the server parts from the client parts. Now that planner is done currently in the compile time, but there are also some runtime optimizations that they do. I think in the future they are planning to make it all, try to do it at runtime as much as possible, so we can sort of skip on the compile step a little bit. Now these bytecodes are essentially sent to, these bundles are then run in two separate VMs. So you have the site runtime. So the site runtime, what they call a site is either client or server, right? So you have one site runtime which is written in Java for the server, and you have one written in Clojure script and compiles to JavaScript for the client. Now both of these runtimes contain a machinery reactor. So the library I was talking to you about, which is the core of Electric Clojure, it is a part of Clojure. It is a part of Electric that handles the execution itself, right? So bytecode is processed and run in the machinery reactor. Now all of this is still pretty high level, right? So to actually write Electric code, so keep in mind that you are going to be writing your regular Clojure code, your regular database code, or whatever it is that you folks do. You sort of surround it with the Electric functions or macros. They have a lot of macros for us to use. Sometimes, rarely, you'll sort of need to get down to using the machinery functions directly, but I believe that is just primarily because of the lack of maturity of the project. I think that's something that's going to be streamlined over time. So going back to our problem statement, right? So if you were sort of thinking about it from an electric engineer sort of perspective, you'd find that you don't need to maintain the state. All you have to do is sort of define it and use regular Clojure code or Clojure script code, and you just use it like you regularly would. Electric takes care of maintaining it for us. So if you have multiple clients connecting to a server, it's going to make sure that it maintains multiple states, one for every connecting client. We don't have to manage any of the network communications because Electric Clojure brings in this property called network transparency, which basically means that Electric takes care of transmitting the state and sort of synchronizing it between the two nodes, in this case the client and the server. We don't have to write any glue code for this because the shape of the data remains the same across the network boundaries. And as an engineer, you're essentially just simply calling regular Clojure functions. You don't have to do anything specific to sort of make this work. Okay. So sort of solves a lot of problems that I've personally had in my career, and I'm hoping that it sort of solves some of yours too. So we saw a couple of examples with it manipulating raw DOM, but that's all cool. But what about the rest of the ecosystem that we all use so much? Currently, and like I said, so Electric primarily works with streaming data. So anything that sort of streams your any streaming DB that is there right now, which is XTDB from Juxt or Datomic Pro, which is recently been made free to everyone. It works pretty much out of the box with that. You don't need to do anything specific. Anything that is non-streaming, like your regular Postgres or MySQL or whatever, it works via PG Notify, which is your regular listen notify infrastructure, which is part of Postgres, or with something third party like ReadySet. So ReadySet is an open source project which essentially lets you register queries and then stream any changes that sort of happen. Works based on CDC. So ReadySet is open source. They also have like a paid version if you're interested, a managed one. It since it has a ClojureScript runtime as well, it sort of works with any JS library that you can use on ClojureScript right now. ClojureScript, if I'm not mistaken, uses the Google Clojure compiler to compile its JavaScript. So some libraries may not be okay with that, but look, if you can't use it with ClojureScript, you can't use it with Electric either, which I think is a fair ask. It works with React, so via I think 2 different runtimes that are available for ClojureScript. So one is Reagent, which I think is the old school one, which I think people still use. There's also UAX, which is fairly new, but I think and I think it's been taken over by some company, I think Pitch or something, who's sort of developing it a lot. There's a community contributed 3JS runtime, which is pretty great. So you can essentially render whatever 3D objects that you want using Electric. And I think most importantly, it works really seamlessly with tests. So Electric repo, and I'll be sharing the link in a bit, is actually fairly well tested. So if you want to look at how do I write an entire end-to-end test for my code and not make it really painful, Electric sort of has useful helpers and macros that let you do this really seamlessly, and you can be assured of confidence on your code. Actually, none of these are official integrations. These are essentially community created wrappers on top of a bunch of the ecosystem that is available. But there's a lot of code snippets that are sort of there. So Electric is in alpha stages, and I think I mentioned it was in alpha 2. Alpha 3 comes with something which is pretty cool. So it's differential data flow. So instead of passing down like the entire environment between nodes and the entire state, differential data flow essentially just passes whatever has changed. And so it basically does a diff and then sends a diff across. So that's something that's going to increase the performance significantly. I think they're projecting. I think what they're seeing is roughly 50 to 80% of savings in just the network traffic, which I think is pretty massive. Otherwise, I think all the stuff that I would like are around making the developer experience better. Right. I think the Slack community is actually like really prompt and like very prompt and very helpful. But I think in order to increase adoption, I think it needs to do a lot more in terms of documentation and tooling around it. I think I'd also like to see more people using it. I think I met a few people here today who have played around with Electric Clojure in the past, probably when it was posted on Hacker News or something. And I think that's fantastic. It was great to talk about our experiences using Electric, what we're looking to do and things like that. I would definitely love for more people to start using it or at least experiment with it. So I spoke to the founder of Electric, Hyperfiddle, the company that's created Electric. So Dustin Getz, and he mentioned that he was aware of at least 9 separate commercial attempts to start off using Electric. And I think there might be more, but he just mentioned about the ones where he was contacted, like only the ones that he was aware of. But there definitely might be more. So I think it's pretty great to see companies starting to experiment with new paradigms like this, and I think it's definitely going to increase the adoption. So, how do you get started working on something like this? I would ask you to go download it, like clone the Git repo, that's the second one on the list, and sort of build something cool with it. Electric, sort of just as a paradigm, lends itself really well to building something real time. Makes it super efficient to build something real time. So if you want to do something like a game or like a board game or any such thing, I think that's a really great idea to start with. Or if you feel like building anything else, like a real time to do list shared with people, that sort of a thing. I think there are a lot of ideas that you can get started with building on Electric Clojure. I think it's just a really cool piece of software to use from experience. It's also like sort of really easy to debug, like because in the server side you can do your regular prints or pretty prints or whatever it is that you use. You can do your regular logging. On the client side, you can, since it's essentially the browser, you can essentially just call console.log and it just works. So you don't really need to do a lot to for debugging and whatnot, but I think more tooling will anyway be really helpful. Like I said, the Slack community is really friendly, and people share their code publicly quite a bit. You can find, if you search that, so that is the Clojurian Slack, which I'm sure like 90% of you will be part of. So the channel is Hyperfiddle. The second is the repo itself. Whatever has been open source so far, I think there are still like 1 or 2 minor pieces that are missing, but I think that'll probably be done pretty soon. The third thing is the examples that I showed you. So I was running it locally. It's also available hosted. I think they host it on some server somewhere. You can go take a look at the code. I found it really helpful. Like I got a lot of tips on the idiomatic ways that they want you to run things just by looking at the Electric Fiddle repo. And the last one is a pretty nice bare bones starter application. Everything is sort of set up for you. So if you want to get started and experiment with Electric, I think that's a pretty good idea. So I would say go build something with it, experiment, and hopefully you can learn a thing or two, or at least let it open up your mind to the sort of paradigm that exists, like apart from the regular client-server communication that you're sort of used to doing, right? That is pretty much all I had. So thank you for your time, and if you want to discuss any questions, happy to do that.